I'll try to stand in front of our camera.
Yep. Yeah, it's right here.
Yep. Okay. Hello everyone. Thanks for coming and thanks for the attendees online. This week is our first week of our ICON weekly seminar this semester. My name is Zhang Wang. I'm an assistant professor in civil engineering and also one of the co-organizers of this weekly seminar series with my colleague Patrick Huynh and Toilette. So we have total of 11 speakers, wonderful speakers this semester. And we'll start with Professor Yan Gu from mechanical engineering. Professor Yan Gu received her bachelor degree in mechanical engineering from Zhejiang University in 2011, and her PhD degree in mechanical engineering here at Purdue in 2017. She was an assistant professor in the Department of Mechanical Engineering at the University of Massachusetts Lowell between 2017 and 2022. She has been with the faculty of the School of Mechanical Engineering here at Purdue since last year. Her research focuses on non-linear control and hybrid system with applications to locomotion. And towards reaching her goal in robotics, her research draws upon non-linear control theory of hybrid systems, dynamics, and optimization to create new methodologies of modeling, state estimation, and control of locomotion. I think that's the topic of this seminar. She received the NSF Career Award in 2021 and the Verizon's 5G Robotics Challenge Award in 2019. Her research on locomotion has been funded by NSF, ONR, ARL, and Verizon's 5G Lab, and reported by various media such as Boston Globe, CNET, Robotics Business Review, and NPR. Now, Yan, the floor is yours.
Yeah. Thank you very much, Ziran, for the wonderful introduction. So good afternoon, everyone. And it's my great pleasure to present my group's research today. And today, my talk will focus on modeling, estimation, and control of quadrupedal and humanoid robot locomotion in non-inertial environments. And I very much look forward to hearing your feedback about our research. Okay, just hold on a second. My screen is frozen. Okay, here we go. So legged robots are robots that use their legs to move around by making and breaking contact with the ground. So if they have 4 legs, they're quadrupedal robots. If they have 2 legs and have a torso and trunk, it's a humanoid bipedal robots. And legged robots have the great potential to benefit a wide range of real-world applications. For example, emergency response, maintenance inspection, agriculture, and home assistance. So now let's take a look at the previous legged locomotion performance. This video was taken about 8 years ago during the DARPA Robotics Challenge. As you can see, the robots failed in various ways. So these controllers and planners work really well in lab environments, but once the robots are put into the real-world environments with gusts of winds and even terrains, the robots just failed in various ways. So why is it so difficult to make robots walk just stably in real-world environments? So one, legged robots typically have a floating base, so their feet are not bolted to the ground. If you push them really hard, they're going to fall over. And second, their dynamics are naturally nonlinear and hybrid. Hybrid in the sense that the dynamics involve continuous motion in the air, the foot swings in the air, as well as discrete contact event when the feet hit the ground. So there's a sudden switch of the state values. And third, legged robots typically have many joints, which means that their state space will be high dimensional. And of course, in the real world, there are always various uncertainties. For example, the winds, the unevenness of the floor, and the sudden pushes from surrounding humans. Now let's take a look at what legged robots are capable of doing today. So these 2 videos show the Boston Dynamics' most famous 2 robots. One is the Atlas humanoid robot, and on the right is the Spot quadrupedal robot. So both robots are able to navigate complicated surfaces. And also for the Spot robot, it's able to achieve precise maneuvering in stationary environments. So both robots can do awesome things that even humans find difficult to do. So the question is, what's next? So Boston Dynamics have been constantly releasing impressive videos of walking robots in challenging environments, right? For people who work in the field of leg locomotion, then what's next? It turns out that there is a new robot functionality, which is leg robot locomotion in non-inertial environments. Although challenging surfaces, for example, stairs, wave field, sand, gravel, snow have been tackled for a long time, there is a wide class of environments people have rarely worked on, which is non-inertial environment. For example, container ships, cruise ships, buses, aircraft, spacecraft, and trains and subways. Lego robots capable of reliably navigating such complicated environments can be used to a variety of applications. So there are 80% of the world trade are carried by ships. And also in the US, every day, there are about 30 million people who travel on public transportation vehicles. So these robots, if they have a capability of navigating non-inertial environments, they could be used for security, inspection, maintenance in these moving vehicles. So for our group, one of our long-term research goals is to achieve safe and autonomous legged operation in non-inertial environments by creating new approaches of modeling, estimation, planning, and control. However, this task is challenging to achieve. It's a fundamentally challenging problem because when the environment is moving, the ground is moving as well, right? So the feet on the ground will also move together with the ground. So which makes the dynamics of the robot not just hybrid, but also time varying, which it makes the control problem very complicated. Before I talk about our recent research on modeling, estimation, control of leg locomotion in non-inertial environments, I will first, let's just dive into the literature and also the performance of real-world robots in real-world non-stationary environments. So first, let's take a look at the literature. It turns out that people have worked on complicated surfaces and environments, but they either assume that the surface or the ground has really small movement, that movement can be ignored, or they only consider constant movement of the environment. So in the literature, there is still a significant knowledge gap in terms of the modeling, estimation, planning, and control of Lego robots in non-inertial environments. Now let's take a look at the performance of today's most advanced Lego robots in a moving environment. So in this case, that's a moving ground. So on the left, we have validated the performance of Vision 60 robots. It's a robot developed by Ghost Robotics in Philadelphia. And on the right shows our performance validation of Digit Humanoid robot, which is developed by Agility Robotics. So in all these videos, you can see when the ground is stationary, the robot is able to walk stably and step in place, meaning it can maintain a fixed location in the global environment. But once the surface begins to move, the robot on the right keeps diverging sideways, and within 20 seconds, the robot loses balance and fell off the treadmill. And on the left, you see when the surface is not moving, the robot was able to maintain a relatively steady posture. But once the surface is moving, the robot's base keeps wobbling, and the end effector wobbles aggressively in the environment, which is not acceptable for manipulation tasks. So for example, if you want a robot to do maintenance tasks on the ship, this kind of wobbling will not be acceptable for achieving high positioning accuracy of the manipulation. So these are the in-lab evaluation we have done, and we believe that these are the world's first evaluation of Lego locomotion in a non-inertial environment. By non-inertial environment, we mean the ground is moving. And what about the real world validation? So earlier this year, our collaborators in UMass Lowell, NRL, NSWC, and NUWC performed the field test on the naval vessel. So we went to Virginia Beach in Virginia, and we boarded Stiletto naval vessel, and the goal is to test the performance gap of Boston Dynamics Spot robot. So we tested various conditions. So but for all the conditions, the sea state is relatively mild. It's a sea state 1. So it means that the wave height is within 10 centimeters. It's about 0.33 feet. And also the ship paths, the ship took various paths, for example, straight and also box paths or zigzag as curves. And the ship speed is between 0 and 20 knots. So 20 knots is about 23 miles per hour, which is relatively fast for ships. And we also tested various robot tasks, for example, standing still, stepping in place, walking with arm folded or extended, and walking in various directions relative to the ship's movement. And we also equipped this testing with various sensors, for example, GoPros, inertial measurement units, and GPS. So now let's take a look at the performance of Spot robot. So in all these experiments, we were running the default controller of Spot. On the left, the Spot robot is supposed to do step in place. You should maintain at a constant posture and constant spot, which is the red dot here. It's supposed to step in place right at that, the green dot, right at the green dot over there. However, because of the ship movement, the robot has to constantly adjust its motion in order to maintain balance. As you see here, the robot wobbles a lot and turning its directions. And on the right, the robot is supposed to follow a green line, which is the center line, the long center line of this rectangle walking region. However, because of the ship movement, the robot just keeps diverging and almost hits one of the inflatable boats inside the ship. So this kind of performance is in sharp contrast to Spot's reliable performance in stationary environments, as we see in previous videos. So why is that? Why even the world's most advanced legged robots cannot handle the ship movement, although the ship movement is pretty mild, right? It's just only 20 knots, and the mild is the sea state. The reason is today's legged locomotion algorithms, either in the literature or on the commercial products, all assume that the environment is stationary, the ground is stationary. So because the algorithms ignore the surface movement will act as continuous disturbances that persistently perturb the robot stability. So that's why the robots are not able to handle these kind of moving environments. Okay, so in today's talk, I will introduce and present our research progress in modeling estimation control, hoping to tackle the challenges and the performance gaps we have identified. So again, there are a few substantial challenges in order to solve legged locomotion in non-inertial environments. So robot dynamics are hybrid, nonlinear, and also the robot's contact point with the environment have constant, persistent, time-varying movement. And also in many scenarios, we don't know the dynamics of the environment. Okay, so here's our proposed controller design methodology. On the modeling level, we explicitly consider the hybrid nonlinear behavior of the robot so that our controller building upon such models will be effective for the actual robot dynamics in the real world environment. And second, we formulate the time-varying interaction between the robot and the environment as a time-varying holonomic constraint, which I will explain later on. And finally, we will draw upon nonlinear control theory and theory of hybrid systems to build provably stabilizing and provably robust controllers to enable reliable locomotion in non-stationary environments. Okay, so first, I will introduce our research outcomes in dynamic modeling. Models are important, right? So especially for model-based control approaches, if the models are not reliable, no matter how fancy the controller is, it will be very hard for the controller to achieve good performance on the actual system. So I will introduce two kinds of models we have derived. One is a linear inverted pendulum model, which is a reduced order model that are widely used in robotics, especially in legged locomotion, and also a full order model. With a linear inverted pendulum model, essentially we treat the robot as a point mass atop a massless leg. And this type of model describes the essential dynamics of walking robots. It's computationally efficient, although it's not as accurate as a full order model, which captures all degrees of freedom of the robot. It's reasonably accurate for today's legged robot design because these robots today's robots typically have a heavy trunk, but like lightweight legs. So approximately they behave like an inverted pendulum. And I will first introduce our previous work on full order modeling of leggy locomotion in non-inertial environments. So with this type of model, we will be able to do stability analysis for faithful representation of the robot dynamics. And then I will talk about our current and previous research of reduced order model of leggy locomotion. And reduced order models are important because they are computationally efficient. Building upon such models, we can quickly plan the robot's desired motion in the face of real-world uncertainties so that the robot can robustly react to real-world disturbances. And existing models all assume that the ground robot contact region is static, which is fundamentally different from what we are going to derive. Okay, so first I'm going to introduce our previous work in full order modeling. So here shows the example of the graph of hybrid dynamics of quadrupedal walking. And in our dynamic modeling, we consider the continuous dynamics when the foot swings in the air. And here the red text highlights the portion we explicitly consider the surface movement. So the second equation here is a holonomic constraint formed at the physical contact region between the ground and the robot. So because the ground is moving, that's why this holonomic constraints is also time varying. And second, we explicitly consider the discrete behavior of robot environment impact event. And this kind of jump behavior is captured by the reset map here. So essentially, if the robot's feet are rigid and the ground is also rigid, so the sudden impact between these two surfaces will cause a jump in the robot's state space, specifically the velocities of the robot. And again, because once the foot hits on the ground, it's going to move together with the ground. So that's why the reset map is also explicitly time varying. And of course, the switching surface that determines when the contact will occur is also time varying because the surface is moving. So here, as you can see, the overall robot dynamics is hybrid nonlinear with the state trigger jumps subject to time varying holonomic constraints. Okay, so that's a full order model. Later on, I will introduce our controller design based on such full order model, as well as our stability analysis for full order model. But I'm gonna take a pause along that line, and instead, I'm going to keep introducing our modeling results, which is reduced order models. Okay, so in the classical linear inverted pendulum model, it assumes that the contact point or the far end of the pendulum is stationary in the inertial frame. But because the surface is moving, we have to relax that assumption. And based on the same assumption as the classical linear inverted pendulum, the leap model, we can arrive, based on physics-based modeling, we can arrive at a second order differential equation, which is linear and time varying. So time varying because the surface is moving. So z double dot, x double dot are the surface acceleration. So you see here, by explicitly considering the surface motion, we arrive at a time varying leap model, which is fundamentally different from previous leap model. If we assume that the robot only has the surface only has vertical movement, and also if we assume the movement is sinusoidal, then this equation will become the well-studied Matthews equation or Hill's equation. And using the existing results from physics, we are able to derive analytical approximate solutions of this second order model. I'm not going to show the details of the model, but all the coefficients have closed form expressions, so we can compute them either offline or online efficiently. Building upon this explicit consideration of the time varying robot behavior, we have also incorporated the hybrid nature into this inverted pendulum model, so which produces a hybrid time varying linear inverted pendulum model. So here, in addition to the second order time varying leap model, we also consider the switching behavior of the legs. So by incorporating such a switching behavior, we will be able, and the switching is essentially caused by foot landing, right? So by explicitly having the foot stepping behavior in the model, we will be able to design a controller for such a model so that we can rigorously and systematically design where the robot should place its foot to achieve robust locomotion. So which is also something I'm going to introduce later on. Besides quadrupedal robots, we have also derived dynamics models for humanoid robots in 3 dimensions. So here I want to point out that all the models we have derived so far are generally applicable for both quadrupedal robots, bipedal robots, or any legged robots with any arbitrary number of legs. So here we consider the 3-dimensional model. We decouple the 3-dimensional robot model into the sagittal plane as well as the lateral plane, the frontal plane. So in that way, we are able to arrive at 2 sets of equations representing the 3-dimensional robot dynamics. Okay, so to sum up our research outcomes along the first direction, we have derived dynamics models that faithfully capture the robot dynamics associated with legged locomotion in non-inertial environments. And later on in direction 3, I'm going to talk about, briefly introduce how we have used such models to design controllers that enable stable locomotion in hardware experiments, and also how we can use these models to analyze the stability of the overall hybrid time varying system. But for now, I'm gonna take a pause and switch gear a little bit and talk about our second direction along this whole line of work, which is robot state estimation in non-stationary environments. So this is a typical setup of our experiments. We have a humanoid robot that is equipped with RGBD camera and also has a Velodyne LiDAR here, which is now shown in this graph. The robot also has an inertial measurement unit that measures the acceleration, angular velocity of the trunk. And all of the joints have encoders that measure the joint angles of all the motors and the joint or the joints. And there's also an artificial contact detector that uses algorithms to detect whether the foot is touching the ground or not. And in this setup, we use a rocking treadmill to represent the moving ground of a non-inertial environment. And usually we will also have a motion capture cameras to record the ground truth movement of the robot to validate our state estimator design. Okay, so the existing state estimator design for legged robots, they usually utilize the assumption that the ground is stationary. That is called leg odometry. So essentially, based on the assumption that the ground is stationary, we can derive measurement models that can be used to correct the state estimates. So for example, based on extended common filtering. However, the standard extended common filtering has an issue that if the filter system is nonlinear, then the filter will be designed based on linearization of the nonlinear filtering system, right? And if the linearization is not accurate, and because we don't know where the ground truth value of the state is, we will have to evaluate the linearization at the estimated state. So if the estimated state and the ground truth are too far away from each other, then the linearization will not be accurate. So which means that the EKF, the extended common filter performance will not be guaranteed. So that's one issue. The second issue is when the environment is non-inertial, the ground is, and most of the time we don't know the movement of the ground. We don't have direct sensing of the movement of the ground. So which means that we cannot assume the ground is stationary, and we cannot use this to form pseudo measurement in order to correct state estimates. So along this direction, we have derived invariant filters to achieve real-time provably convergent estimation, even when the filtering system is nonlinear. And also we explicitly consider the fact that the ground is moving. So these are the 2 key novel points, contributions of this work. So the invariant filtering is a filter design on matrix V groups. So instead of representing the state as a stack of numbers in a vector, we use the matrix to represent the state vector, which includes orientation of the trunk, linear velocity of the trunk, the position of the trunk, and the position of the foot. Yes?
You assume that the velocity of the environment is known?
Yes, in this work, we assume it's known. Yeah, that's a great point. So far, we still assume that we know the movement of the ground. Okay, so and also we define the right invariant error by multiplying the estimated state with the inverse of the ground truth. And here's our process model. In the process model, we explicitly consider the movement of the ground, and we assume we know the movement of the ground. So it turns out that this system is group affine, which means that the deterministic log error equation is independent of the true state and linear. So which means that if we design a filter on the matrix Z group, although the filter system in Euclidean space is nonlinear, it becomes linear on the matrix Z group. So no matter how large the estimation error is, we are always designing the filter based on an accurate model of the error system if the system is deterministic. Okay, and because Legge locomotion is hybrid, right? So in the process model, we also consider the switching of the foot. And it turns out that this switching map is a group action, which means that this is an identity error jump map. So error doesn't jump on the matrix Z group. Although in the usual Euclidean space, the error jumps, but on matrix Z group, it doesn't jump, which is another nice property of this formulation because we don't need to consider the jump in the stability and convergence analysis of the filter design. We only need to consider the continuous portion of the dynamics. And also based on the observation that the foot and the ground share the same normal vectors, we can form a measurement model, which turns out to be right invariant. So therefore, the local asymptotic convergence is probably ensured for the hybrid deterministic system. Okay, so here shows our validation results. We tested humanoid walking on the rocking treadmill under large initial errors. So we consider velocity error in 3 directions. And in each direction, the error is between -1 meter per second. It's a really large error. And also the orientation error is between -30 degrees and 30 degrees in each direction. But still, as you can see in the plot on the next page, this is our proposed method. The error, we're able to drive, the filter is able to drive the error to really close to the ground truth, which is a thick red line within half a second or almost 1 second. And also once the surface begins to move, the yaw angle even becomes observable. But with the previous approach, the yaw angle is not observable and the convergence rate is not as fast as our approach and the final error is not as small as our approach. Okay, so with this work, the contributions are we find a way to treat the movement of the ground in the filter formulation. And also we consider the hybrid behavior in the filter formulation. However, as Kevin just asked, in this work, we still assume that we know the surface motion. And right now, we're tackling the problem where we are formulating the filter without relying on measurement in the world frame, without relying on the measurement of the surface. So that's something we have been working on actively. So hopefully we will be able to come up with a filter that is invariant to the surface movement as well. Okay, so the next direction I'm going to introduce is about controller design. So we have derived state estimators that can provide the values, reasonably accurate estimates of the movement state for the robot. And also we have derived models, both full order models and reduced order models that can be used as basis for controller design. So now I'm going to introduce our recent efforts on controller design. Okay, so after we designed a nonlinear controller for the continuous phase of the robot dynamics, there are various nonlinear techniques, nonlinear control techniques we can use. So for example, inflow-output linearization. We will be able to linearize the continuous phase dynamics into a simple linear time invariant model. However, because of the surface movement, which is time varying, and also the desired trajectory for the robot to follow, which is also usually time varying, the reset map of the robot, which corresponds to a sudden jump in the robot's joint velocities after foot landing. So the reset map is time varying. It's not just time varying, it's uncontrolled because impact occurs instantaneously. There's no way for us to instantaneously change the behavior of the robot, right? For the real world robot. And also the reset map is nonlinear. It's a state triggered, meaning when the foot reaches a zero height on the ground, that's when the jump occurs. So how do we guarantee stability under such complicated impact behavior? So we have derived stability conditions based on the construction of multiple Lyapunov functions. So the idea is during the continuous phase, if we can ensure that the error converges exponentially, then even if the error jumps across the uncontrolled impact behaviors, as long as we can ensure that overall the error, the discrete sequences, right, the discrete sequence right after the jump is strictly decreasing, then we can still ensure that the overall hybrid system is stable. So we have converted such stability conditions into conditions that we can directly use to guide the controller designs. And here shows our first results of controller design. So in this work, we still assume we know the surface motion accurately ahead of time. And given the surface motion, we plan the robot motion ahead of time for the entire history from 0 to however long we run the simulation. So on the left, it shows that our previous controller design for stationary surface is able to sustain stable walking on stationary surface. But once the surface begins to rock, the robot becomes unstable. And on the right-hand side, by incorporating the time-varying aspects in the model and update our controller design based on the time-varying model, we're able to achieve stable walking on a dynamic rigid surface, which is in a non-inertial environment. And here shows our experimental results. We have tested the controllers under various surface movements, and we have also tested a case when the surface motion has a relatively small uncertainty. For example, the belt speed of the treadmill has an uncertainty of 2 centimeters per second, and the pitch amplitude of the rocking treadmill has an inaccuracy of 10 centimeters. So that's a peak-to-peak height right under the robot's support foot. Okay, so this we believe constitutes the first experimental results in the literature of stable leggy locomotion on non-stationary surfaces. But still, there are lots of things we need to do. First, we assume that we know the surface motion accurately. And also, we plan the motion offline for the entire history. So both assumptions are not realistic for real-world deployment. So that's why later on, we have exploited our reduced order models to enable online motion planning. So we still assume we know the motion of the environment, the surface accurately. But in this effort, we plan the motion in real time, utilizing the reduced order model we have derived. So specifically, we use the reduced order models and the analytical solution we have derived to plan the desired motion of the robot in real time, and then feed the desired motion to the lower level planner to map all the desired center mass trajectories into individual joints. And then these motions will be executed by the robots, all of the motors of the robots. And here shows the validation results of our planner efficiency. If we use a numerical solution to plan the desired motion for 2 seconds, the walking motion of 2 seconds. In MATLAB, it takes over 1,000 milliseconds to plan the motion of 2 seconds. In C++, it's a little bit faster, 70 to 72 milliseconds. But if we use our proposed analytical approximate solution, we are able to plan 2 seconds of walking motion within 10 milliseconds, which is fast enough for real-world motion planning. And again, this kind of fast planning efficiency is important for achieving robust locomotion under uncertainties, because when there are large uncertainties, the robots will have to replan its desired motion in order to reject the disturbances, right? So we need to have this fast planning speed in order to enable online motion planning. And here's shows our validation results in both realistic simulations and as well as hardware experiments. So here shows the real speed of the experiment. We move the robot away from the center to the edge of the treadmill so that the movement the robot experiences is even more aggressive. So here the peak acceleration of the ground is about 1 meter per second square. So it's relatively fast. Okay, but still in this work, we assume that we know the surface motion, which is not realistic. So that's why my student, as you see here, Amir, is working really hard and trying to relax this assumption. So we came up with a new controller design. In this controller design, we no longer use the previous continuous leap model. Instead, we consider this hybrid reduced order model so that we can rigorously and systematically plan the footsteps to achieve robust locomotion. And here we no longer assume that we know the accurate surface motion. We just assume that we know a bound, a range of the surface motion, a limits range of the surface motion, and which is in our validation and algorithm formulation, we consider a really large bound, which is between minus and plus g. There's a gravitational, yes?
They put bounds on the acceleration.
Yes.
Yeah, the acceleration.
On both the amplitude and the, so here we are still considering vertical movement, and we consider a bound on the magnitude of the acceleration. So it's plus minus g. Yes, the magnitude of the surface acceleration. Yeah, thank you. So here we consider a generous bound. So it's plus minus g. So plus minus 9.81 meter per second square in our validation. So in the theoretical formulation, it can be any large number as long as the foot can still sustain, can still keep a stable contact, can still keep a contact with the ground. If the acceleration is too fast downward, then the robot will lose contact with the ground, right? And based on that generous bound, we have derived provable robust stability conditions for the general time varying leap model. And Amir has found out a way to convert this condition into linear conditions on the leap state so that we can formulate a quadratic program. And we can solve this program, quadratic program in real time to achieve fast online planning. So again, we care about full stack planning because that's how robots can use to sustain stability. If you push a robot really hard, it will take a few steps and catch its body to maintain balance, right? So that's why we care about full stack planning. Okay, so here shows our validation results. So this time we tested the robot locomotion on various surfaces, not just a flat surface, but also pebbled surface. And in this case, we're not just considering the periodic motions in all of previous videos I showed. Instead, we consider aperiodic surface movement. So you see the magnitude and direction of movement is aperiodic. And the robot doesn't know the precise profile of the surface movement. It only knows the magnitude of the surface acceleration at the footholds. And also it uses the stick to poke the robot and check its disturbance rejection capability. And here we really push the limit of the robot. The robot, its own weight is about 30 pounds and is carrying a 10-pound load. And it's unknown to the robot. While the robot is walking on a glassy surface, and the robot is not aware of the changing friction coefficient in the environment, but still the robot, while the surface is rocking, but still the robot is able to sustain robust walking. And we also, not in this specific video, but probably early on, we also added sway perturbations to the surface movement. So that's also unknown and unmodeled in the planar design. But in all these cases, the robot is able to sustain stable walking, and we didn't manually tune the parameters. We just used one set of control parameters and planar parameters, and they're able to handle all these various cases. And we also compared the performance of the controller, our proposed controller, with the baseline controller, which is a green line. That's the controller equipped on the robot, and also a blue one. The blue one is a proprietary controller, and the baseline one, the green one, is a controller that is widely used in the community, which is developed by MIT for the Cheetah 3 robot. And among these three controllers, our controller achieves the slowest divergence, and eventually it diverges a little to maybe about 20 centimeters, 15 centimeters, because the state estimator drift. We just use the onboard state estimator of the robot, which assumes the orientation is constant, but in this case, orientation of the trunk is never constant. Okay. So far, I have introduced our controller design and validation efforts on quadrupedal robots. As I mentioned earlier on, our controller design can be used for humanoid robots as well, because quadrupedal robots, humanoid robots, at the end of the day, they are both hybrid systems with state trigger jumps. So in principle, the controller design method should also be valid for humanoid robots. So that's why we have also looked at the controller design problem for humanoid robots. And in this specific effort, we consider the hybrid time-varying inverted pendulum model, and also we consider the three-dimensional one, because the humanoid robot has a significant movement in both sagittal plane and also the frontal plane. I'm now going to show the details of our stability condition. So the slight difference between this setting and the previous one is, in the previous work on quadrupedal robots, we consider the vertical movement of the surface. So in this work, we are considering the swaying surface of the movement. And the motivation for us to consider this is, if we go back to the very beginning of today's presentation, we have spot this severe performance gap of digits proprietary controllers. It's one of the best commercial controllers. And you see, even under mild surface sway, the robot keeps diverging sideways and eventually fall off the treadmill within 60 seconds. So we are very curious about how to sustain. So it turns out that our controller, quadruped controller, can already handle mild sway motion. But what about the humanoid robot? So that's why very recently, starting from last year, we have started to look at the controller design for humanoid robots. The different thing in the model between this swaying surface and the vertical surface is, when we just consider the vertical movement of the ground, the robot dynamics is homogeneous but time varying. If we're considering the swaying surface but not the the vertical motion, then the robot dynamics is non-homogeneous and time varying. So there's a fundamental difference in the model's property. And for this general model, we have also derived stability conditions. Fortunately, it's a linear system, so we can derive closed form stability conditions. So essentially, we consider the monodromy matrix of the hybrid system, and then we check the eigenvalues of the monodromy matrix. If their magnitudes are less than 1, then the system is stable. So we're able to derive closed form solutions for such general models, as well as the stability conditions for such other models. And we use the stability conditions to inform the controller design to ensure stable walking. And now I'm going to show some very recent results. On the left, it's a slowed down version. So our controller is able to make the robot walk stably in 3D environment. So that's a Miyojoko environment. We are simulating a swaying surface. On the right shows our new lab in Powder. We just received the treadmill last month, and the robot arrived a little bit early on, but we tested the surface motion 4 centimeters and 1.12 T. So the robot is able to walk stably on the surface. So there's a human operator right behind that. He's not holding the robot, it's just trying to catch the robot. So both the robots and the treadmill are too expensive. So we have to have a subject on the robot to catch it. Okay, and we wanted to take a video from the sideway, but before we got a chance to take the video, the robot broke down. So hopefully in the future, it broke down after 1 month. It's almost 2 months. Right now the robot is okay now. Yes, we sent it back to Oregon and they have fixed it. Yeah, so the battery was broken, the heap circuits was broken, and the emergency stop was broken. So yeah, just within 24 hours of experiments, the robot was broken in various parts. So it's really hard to do experiments, and yeah, these are the hard work from my students. So next time we're going to shoot a video from sideways, so we will see the humans are now actually holding the robot. Okay, so that's all the technical content I wanted to present today. So in terms of the future work, ideally we want to make our robots, eventually we want to make our robots walk stably in a non-inertial environment with arbitrary ground movement in 6 degrees of freedom, rho PGL XYZ. and the robot doesn't know the movement of the surface. And even more even more challenging scenario is for state estimation. If the robot is inside a concealed ship, it won't be able, a concealed ship or a space machine, it won't be able to see landmarks attached to the ground of the Earth. So then in that case, how can the robot figure out the accurate state estimation, right? How to solve this problem, because it loses the landmarks with respect to the inertial frame. So these are some of the ongoing questions we are solving. And also we are interested in combining manipulation with locomotion to solve local manipulation problem in challenging environments such as non-inertial environments. With that comes to the end of today's talk, and I'll be more than happy to take any questions. Thank you. That's sorry. Yes. Yeah, the robot fell down. Yes. And actually, when we test the Boston Dynamics spot robot on ship, the spot also fell down. But I didn't show that, show those videos.
Landmarks in the ground, but we could look at landmarks on the ship. Now, I know they're not inertial, right?
Yes, they're not inertial.
So we consider used for somehow.
Even yeah, so we know some of the ships has those horizontal bars, really large horizontal bars for aircraft to land on a rocking ship. Those could be potential landmarks we can use. Maybe the horizon could also be helpful if the ship is not moving too fast. Yeah.
Stabilize itself on the platform before the gravity speed would be able to stabilize.
Yes. Leo here actually tried the rocking and swing treadmill. It was easy breezy for Leo to maintain balance, but it's really hard for robots. Yes. Yeah, absolutely. Yes. Yes. Yes, absolutely. Yes. Yeah. We need to cleverly get the AirB approved. Yes. Yep.
Great talk. Thank you.
Yeah, thank you.
Couple of things curious just to understand. So at the end, when you find the controller, you're finding the close-up instruments, or is it you're basically still using the low-level controller?
Yeah, that's a great question. So for this experiment results, we actually derived, we built our own low-level controller.
Right.
That's another QP-based controller,
Yeah.
not based on the linear inverted pendulum model, but based on the rigid body model, which is a more complicated version of the robot model.
You use like the control the output functions, or you do like this?
Yeah, we just use the QP-based controller. Yeah, we didn't use control the up and down function or control barrier functions, but that could be our future work. Yeah, for the humanoid robot, we are also implementing our own low-level controller. It's more like an inverse kinematics-based controller. Yeah.
Another question is that to become non-inertial, it should either accelerate or decelerate.
Yes.
So for the ship, when you said that it's actually 20 knots speed constant, that if there's no wave, I mean it's not inertial.
Yeah, right. Yeah, exactly. Yes, exactly. So in all the cases we tested, the ship average speed is 20 knots, but still the ships like draw boxes or also do zigzag. And although the wave is pretty calm, just the sea state 1, but still the ship rocks. And even humans will rock, will wobble a little bit. Yeah, I actually just came back from another field test last week. I went to California to do another testing of Lego robots on. This time it's a commercial ship. So even on that day, the sea state was it's also about sea state 1, but still humans can get. At least I was a little bit sick because of the rocking motion of the boat. Yeah.
One more question.
Yes.
Very, very interesting. So
Thank
I
you.
think the non-inertial frame, you can get it either from just accelerating or decelerating, but also it's kind of confined and it's like that.
Yes.
Circular. Is
Yes.
there any treadmill that is actually
Yeah, we don't have that. We don't have a treadmill like that. Yeah. Yeah. So actually we have been thinking, yeah, sorry.
Very curious.
Yeah, we don't have that, but we have been thinking about how to build portable moving surfaces that is low cost and small scale. So we can run these demos wherever we want. So we haven't like come up with good ideas yet, but if we can come up with a portable, a small size, low cost platform, then maybe we can move the platform in a circular way to emulate the moving surface.
The last question is, I think this work is great, and that you already showed proof that stability given the.
Thank you.
Predictions.
Yes.
Is there any way to classify the more quantitatively how non-inertial works, so that you can actually test it on the way that at how much that the proposed controller actually work? Because like a lot of system that has its own put limits. and stuff.
Yeah, right.
So maybe the maximum accelerations given that situations, what's the rating of it? Because is there other researcher actually looking into this non-inertial thing other than the.
Yeah, I think for Lego robots, our group is, I'm not aware of many other groups. I know there's a group in Germany. They have some previous work. It's Germany's NASA, is DLR or DRL. They work on DLR. Yes, DLR. Yeah, they work on rigid surface with a constant speed, which is different from the non-inertial environment, right? And also recently, I know Dr. Ye Zhao's group, they recently started to work on this moving surface. But the difference between our work and Dr. Zhao's work, at least for the moment, is they consider the sudden movement of the surface, but we consider the continuous, persistent movement of the surface, right? But I believe this is an area, perhaps an emerging area that more and more people are interested in. So for example, I know there are some researchers, engineers from Navy, they're interested in having wheeled robots to operate in rocking ships. So last week we tested wheeled robots on the rocking ship, and even for wheeled robots, it diverges really quickly, even under mild ship movement, because it also, the ship motion confuses its state estimators and controllers. And they use the wheeled robots, for example, to transport aircraft on carriers, on naval carriers. Yeah. So yeah, but I think the benchmarking will be a very interesting and meaningful direction we can work on. Yeah, thank you.
Here's a better line. So earlier when we were talking about the theoretical results, you mentioned that one of the assumptions was a sinusoidal signal. Does that need to be like a pure sinusoid, or can it be a combination of sinusoids that you can keep in close to Fourier analysis?
Yeah, that's a good question. So this expression, I mean, our analytical solution is for the case when the vertical movement is a simple sine wave. It is if it is a periodic motion, then we can approximate it, as you said, as a summation of sine waves. And then I think using Flow-Kit's theory, we should probably be able to still derive the approximate solution. For example, using the fundamental matrices, which is numerically compute those matrices to get the approximate analytical solution. But again, later on, we just relax all these assumptions. We just consider a bound on the acceleration.
Cool.
Yeah.
And that's in the application.
Yep.
I'd be curious if there would be any way to actually maybe treat the non-inertial signals as like you think of a sound signal, and you can kind of decompose it into its base parts, and maybe estimate potentially just via what it senses the changes, and use by like Fourier analysis. Of course, I don't know all of everything that you already done, so
yes,
that could be a dumb idea.
I see. Oh, I mean, I think that's a promising direction we can look into. I know there's a vast literature in the ship motion analysis and wave motion analysis. I think there must be something, yeah, we can draw upon. Yeah, thank you. Yes.
The tip of the wave movement, is that like very periodic and like?
Yeah, it feels periodic. It feels it keeps the rocking with a constant, at least for maybe 10, 20 seconds. It feels periodic.
So it's
Yeah.
kind of like locally periodic then?
Yes.
You could somehow sense the acceleration.
Yes,
Could that help
yes.
predict the future wave movement?
Yes, exactly. So that's something we're also looking into. So if you can predict the surface movement, then we can build, for example, model predictive controllers. Yeah, that's a good idea too.
You want the robot also to be able to stabilize itself. It can be shifted.
Yes.
Not just move the wave.
Yes. Yeah, we want to handle both translational as well as rotary motions of the surface. Yes, Kevin.
I understood your state estimation section correctly, you have this non-linear estimation problem.
Yes.
Your state as a vector, and you transformed it into a matrix, and suddenly the estimation problem became linear. Is that right?
Yes.
Can you explain a little bit about
Yes.
that?
Yes. So there's a recent advancement in state estimation. It's called invariant filtering. And based on the methodology of invariant filtering, we represent states as matrices. So it's a matrices on Lie groups. And if the process model, it can be linear as long as its group affine, it satisfies certain mass model conditions, then we can make sure that the error equation for the propagation step based upon the process model will be linear and independent of the true state.
Okay, so what is it about? Do you have some intuition physically what it is about the robot's dynamics that fit this sort of nice?
Yeah, right. Yeah. So I think the reason is, so essentially this process model is the motion dynamics of the MU, and the MU is fixed to a rigid body. So essentially we're just considering the rigid body motions, the 6D rigid body motions, and they naturally have those nice properties on matrix Lie groups. Yeah, and they carry over to the state estimation problem.
So your state is this matrix, and you've got all these fixed zeros and ones in it.
Yes. Yeah, that's just the structure of the elements we construct, and it turns out that it belongs to the group SE3. So these are the elements we need in order to make sure that the state is on the matrix Lie group. But essentially, these are the physical variables we are interested in. As yeah. Yes. Yeah. So it will satisfy the conditions for that group. Yeah.
Oh, by the way, I think you have some motorcycle gear on your robot.
Motorcycles?
Yeah. Like jacket and a helmet.
Okay, yeah, we should consider doing that. Yeah, maybe we can borrow yours. Yeah. Yes.
So, kind of building off a couple of the earlier questions, have you thought about like how you could, and maybe it would be too related to the other research you mentioned, but what about like sudden like appearance of a perturbation or a slow decay of it, like thinking about natural disasters.
Yeah.
Like an earthquake.
Yes.
So if you had that and your robot's walking along, it's happy, and then it hits an earthquake and you don't want it to die.
Yeah.
Like, could you turn on your controller and learn the sinusoid, and as it dies out, or I don't know if earthquakes are actually sinusoid, but whatever it is, and kind of apply your ideas in that application.
Yeah, I think our approach is promising to be extended to solve those problems. But we haven't solved the sudden perturbation, that problem particularly yet. Yeah, right. Yeah, that's a good suggestion. Thank you. Yep.
Adding more to Phil's suggestion,
Yeah.
I think that's like depth oscillations. So
Yes,
instead of-
depth
instead of having
oscillation.
So you just make it to have a depth oscillations.
Yes.
Then it naturally kind of stop,
Yes.
kind of became exponential.
Yeah, right. Yeah, there might be some existing work in physics. Yeah, probably. Yeah. Yes.
How does that contact detector work?
Yeah, so the contact detector, so this contact detector is also one of the reasons we guess the robot couldn't handle the moving surface well. It's just an algorithm. So we know F equals ma, right? F is the ground contact force that provides the driving force, some of the driving force for the robot to move around. So based on the encoders, we can get the accelerations of all the joints, and the IMU also returns the acceleration of the base. So using F equals ma, we can use dynamics to estimate the ground contact force. But that's not accurate if the surface is moving.
So you don't
Yeah.
have a sensor. You don't have a sensor.
Yeah, this robot doesn't have a sensor for that. No. Yeah, they just use because sensors are usually expensive. Those kind of sensors are usually expensive.
Currents that have a spike.
Yeah, I'm not sure how they are.
Sensor that has a spike. So the power check the spike, which depends.
Yeah, right. So for us for the humanoid robots, we still just use their default contact detector. Yeah, we still use a contact, but it's not very accurate. So we need to do some tweak when we do experiments. Yes.
Basically, the contact detector, even if there's a slipping, does the algorithm need to change or it will remain the same? So even if there is slipping, you can just calculate the forces and like everything should remain the same, right? Again, like if the friction coefficient is too less, so if you are assuming that there is no slipping, then there is an algorithm irrespective of friction coefficient. If the friction coefficient is below a certain value, there will be slipping. So do you need to change your controller or your equations a little bit so as to make the robot move even if there is slight slipping? Because in one of the videos I saw there was slight slipping.
Yeah, so we are not addressing the sleeping issues yet. We just assume that the sleeping is small enough for us to ignore. But that's an important question we should address as well.
And
Yeah.
the other thing is that like what I'm thinking that all the oscillations kind of move the attitude of the robot is actually motion capture cameras, right? But like this primary application of these robots will probably be in industrial setting. So industrial setting you will have like lot of machines which are surrounding robot, and there may not always be a line of sight from the camera to the robot. So in that case, like, if you probably need some accelerometers and etc. so that you can predict how each joint is moving. Depending on that, you can calculate the orientation. But will the errors because of those sensors will be will they be too large that it will make it inaccurate, or will it be okay? Like, can you just without the motion capture cameras, can you use this robot using the same robot?
Yeah. So again, we're not using the motion capture cameras to inform the controller. We're just using that to get the ground truth, to monitor the robot motion, but we don't use it to feedback to the robot. We only use onboard sensors to inform the controller and the state estimator. Yeah. Yep.
Any more questions from the audience?
Yes.
One-legged robot.
One-leg robot? Oh, one-leg robot. Yeah, I think one-leg robot will have to do hopping, right? I feel hopping might be easier than walking, because hopping if it's a brief contact with the ground, and for majority of the time it's in the air. You can adjust its movement and adjust the landing point. There are some hopping, subtle. Yeah, subtle. Yeah, it can jump really high surfaces, and yes, yeah. I feel hopping might be easier than walking. Yeah. Yes, there is always contact with the ground. Yes. And the contact is complicated. In all the work, we assume that the robot has a relatively secure contact with the ground, but if bad things really happen, the robot's foot can contact the ground in various ways. And this contact uncertainty can be really tricky to handle. But if it's a hopping, then the robot is in the air. It doesn't have these contact issues, uncertainty issues. Yeah, right. Yeah, exactly. Yeah. Yep.
Did you footstep timing too here?
Yes. So for the robust locomotion control one, we plan the footsteps in real time. We have a pre-planned footstep sequence, but we adjust them in real time. Yeah, in order to ensure robustness. Yep.
No questions about mine.
Yeah.
Yep.
So let's thank the speaker.
Thank you.
So feel free to catch up with Professor Gu offline. And our next week's seminar is actually going to be on Thursday,